So the first, so let me say remind you a little bit about the purple table. The left-hand side says, if I have something, how do I use it? And the right-hand side says, if I want to prove something, how do I prove it? Right? You have some axioms you're starting with, and something you want to prove. And so you can either start hacking from what you have, saying what can I apply to that, or you can say this is where I'm going. How do I go backwards? Right? So usually, not usually, I mean quite often at least, what I'm getting you to prove is an implies. Why? Because it's hard to prove things just out of the blue. And if you want something to be true in every possible universe, then you're going to need some assumptions. And the way we get those assumptions usually is by an implies, right? So here you can see it's bracket implies bracket, right? So you can ignore what the brackets are right now. You just see that this is an implies statement. And you look in the purple table under implies, and it says you do it by deduction, right? So we know the structure. We're going to start off by saying, hey, what is it? We're going to use deduction. What is our goal? And so we state what we're trying to prove by deduction. That's line 1. And then line 2 assumes what's on the left-hand side, right? Because if what's on the left-hand side is false, then what we're trying to, the implies is automatically true, right? So we're going to handle the case where what's on the left is true, right? So here we're assuming it's true, right? And you'll see we come all the way down to line 13. Our goal is to prove the right-hand side, right? And once we get the right-hand side, then line 14 will conclude the deduction that left-hand side equals right-hand side. All right? So now what we're trying to do is we'd have line 2, which are our assumptions. And from line 2, we want to get line 13. Right? And so we can either hack down or hack up. And let's start at the top. It says we have an and. All right. So how can we use an and? It's sort of a big complex structure, which we're not going to be able to use to get to 13 by itself. Right. So you look in the purple table under and it says, hey, if you got an and that you want to use, maybe you should separate it into 2 separate things. All right. So line 3 and 4 separates out the and into 2 statements. Yeah. Right. And then we want to think. So now I would say it's kind of hard what to do, right? I think maybe, did I even give you the hint? Yeah, because I would say now you need sort of a leap out of somewhere as to what to do next, right? It's not clear what to do next. I mean, on the one hand, if we're going forward, right, what we see is line 3 and line 4 are both ors. And what can you do with ors? You look under the purple table under ors, and you got selective or, which means if we know P or Q and we know not Q, then we can get P, right? If you know one of 2 things is true and one of them's not, you can get the other, right? But we don't really seem to have that here. So if you look under the purple table again, under or, the only other thing it lists is by cases, right? And I gave the hint do proofs by cases with P or not P. Now, the chances are if you did cases by something else, it would probably fall out as well, right? I mean, in some ways what we're doing is what I call Davis-Putnam tree, right? We don't know how to solve the whole thing, so we choose some variable to split on, right? And I chose P. Now, why did I choose P? Well, quite frankly, it's because P appears in two of my ors, right? So it's going to give me more power. And in fact, the other thing I can kind of see is that P is negated one and not negated in the other. So no matter which way we set P, one of those guys is going to get hit, right? So my insight was to do cases on P, but I told you that, and quite frankly, there are two reasons I told you that. One, so that you won't panic and drown, and two, it makes the marker's life easier if everybody does basically the same thing, right? So by giving little hints, ideally everybody's answer will be more or less the same, and the TA will be able to bang them off, right? So, in fact, yeah.
Is the purple table?
No. In fact, the text is at the printer, so now I can say with authority, you will not have to have memorized the purple table. But a bunch of us were talking about it, and we came up with a compromise, and the compromise is you won't have to memorize the names of the rules. All right, so I will say, for example, what is proof by cases? And you will have to know proof by cases is I have two cases. So I need to, in fact, my recommendation is that you don't just memorize what's in the table, right? You should really kind of understand it in your soul so that your subconscious can help you think deeply about it, right? So what's proof by cases is you're going to have two cases, right? And if the one, right, let's call them alpha and beta. So if the one case is true, if alpha is true, you get gamma, which is what we're looking for. And if beta is true, you get gamma, what we're looking for. What do you also need? You need that there aren't other cases, right? That alpha and beta is enough to cover all possibilities. So you need to know that alpha or beta, right? So you will have to, on the test, I will tell you the names of the rules, and you will have to fill in certainly the math and you know, quite, you know, and the meaning. You should know the math and the meaning, right? Everybody got that? Right, so in this case, we know we're doing proof by cases. So we go ahead and do it. And what are we trying to prove by cases? Well, we're still trying to do our implies. So what we're trying to prove is R or Q. So we're trying to prove R true by cases. And I tell you what the two cases are, right? Line 5 says, what are we trying to prove? What our cases are? All right, so to prove by cases, we have to have three statements, right? The one statement is the or of our cases, right? So how do we get the or of our cases? Well, it's P or not P. How do we know P or not P? Food and metal gives it to us, right? And at one point, in some version, in fact, the Davis-Putnam version of my purple table, we focus proof by cases into saying well, you're doing some variable in its middle, and so we'll give in its negation. So we'll give you excluded middle for free, right? But to make it more general. All right, so we get line 6 is that one of the cases is true. And then we have our two cases. So here I'm saying, let's look at case P. So when I say case P, right, I'm automatically kind of saying, see, line 7 says we're assuming it, right? How are we assuming it? It's kind of deduction. We want to prove, remember what we want to prove, that if it's case P, then we get what we want, right? So that's kind of an implies, right? We're basically proving if P, then you get R or Q, right? The right-hand side. That's what we're trying to do. So how do you do it if you assume P? And instead of saying deduction, I worked it right in to say our case is P, so we're assuming P, right? Now, if we know P is true, right? We look up at, we go back and we see our two clauses, 3 and 4, right? We have two ors, and they both have P's in them, right? So, and we know P is true. So we can plug in P is true into the two clauses and see if that helps us, right? And if we plug it into line 4 says P or Q. So if you plug in P, okay, what do you get? You get, okay, line 4 is true, but we already knew it was true, right? Knowing P is true gives us that line 4 is true, but line 4 is true. It's not very useful, right? We plug it into 3. 3 says either P is false or you get R, right? Well, now what rule do we use, right? We have an or, and you look up in purple table what you do with ors, and it's selecting or, right? It's selecting which one's true. You need to know one's true or the other's true. So you select one is true by eliminating one of the cases, right? So line 8 says we're going to do selective or from line 3 that says not P or R, and line 7, which says that P is true. And what do we get from that? If not P or R, well, then R must be true, right? Now we know that R is true, and that's really pretty good, because where am I going? I'm going to R or Q, right? So from R, what do I do? Well, it's hard to know what I'm doing from R. So I then flip to where am I going, right? Where I'm going is R or Q. And if we were going backwards, how do you prove R or Q? Well, you look up R. If you look up in the purple table, how do you prove an or? It'll tell you the way you prove an or is it's sufficient to prove one of them or the other, right? If you prove Q, you've got it. You prove R, you've got it, right? By building, right? So now we have our R. So we line 9 is we take the R and we build it, evaluate, right? We know the value of R, so we're kind of evaluating, right? We build R or Q, right? And that's fantastic because that's what we wanted to get, right? For proof by cases, we need to prove that in our first case, we get what we want, right? Does that make sense? And then the second case is the same, right? And then we proved our two cases, so we're done, right? And then see line 13 is our proof by cases. And we have line 6, which is our or, our line, then we have kind of our one case. I called it line 9, right? It's really kind of line set 3 to 9 is our first case, and 10 to 12 is our second case. Right? People buy that? Could you all do one of these? Because this is about the level of difficulty. You're going to have to do 2 of these, and they're both about this hard. Yep.
Like you had not P and not P didn't give you Q. Like,
right.
You still would it still work? Wouldn't this mean that because if you have R from P, that you can say like R or Q, because but if you had like not P and didn't give you anything, then
right.
would this proof be false? Because it's only true under if P is true, and if you don't know if it's P is false, you don't know if it'll work.
You're trying to say in all possible cases that might arise, how do I do it? Is that the question?
If you had not P and not P didn't give you anything, would this still fine?
Yeah, so I'll tell you something that always works, right? And I only want you to kind of do this at really last resort, because I definitely know how you do table lookup, and usually I have a proof in mind that I want everybody to get, and so I set it up so the proof in mind follows from the purple table, right? But if you really can't do it, you can always resort. If you resort all the way to table lookup, my advice is to give 0, but a middle ground is to do Davis-Putnam, right? So I have something I want to prove, and I branch on P or not P, right? And now I need to prove this case, right? And I take this statement and I substitute it P as false, and I get some simpler statement I'm trying to prove, right? And right, I added into the purple table ways of helping you simplify, right? And now I have this simpler thing to prove, and that's kind of what we did here. It was simple enough that we got what we wanted. But you're saying, what happens if we panic here? We don't know how to do this, right? Well, if you really don't know how to do this, well, then you could branch on another variable, right? And then in this case, plug both variables in and simplify, right? And you keep going until you get something that you can prove, right? So, if your Davis-Putnam tree is a full tree, I mean, how do I know this is always guaranteed to work, right? Because worst comes to worst, you do a full binary tree on all your variables, right? And then each path, right? We have n variables, and there are 2 the n paths, and each one sets the variables in a certain way. And when you set all those variables, then what you're trying to prove, well, you've set all the variables, so you're evaluating, and it's either true or false, right? And so what are you basically doing? Table lookup, right? And so if you did an entire tree, you would be doing table lookup, which is, I was kind of saying, is worth 0, right? So the less like table lookup, the better, right? Here, we're doing a little table lookup, right? We're splitting it into P and not P, because I just didn't know what to do otherwise, right? Does that make sense? Any other questions, anybody? Yes.
We start with R location and then go back.
Well, from backwards, I would look up in the purple table, how do you prove an OR? And I would see, to prove an OR, I have to either prove the R or prove the Q, right? So then I might narrow my thinking to how am I going to prove an R, right? So here now I got not P or R, and I have P or Q, and where do I want to get? I want to get R, right? So then I think, what am I going to do in between? Well, this doesn't mention R, so it's not likely to help, right? So then I'm going to say, well, how do I use this? Well, I mean, I can't really go backwards from R because it's nothing there, right? But from this, how do I go forwards from this? Well, to prove R, well, clearly I have to prove that this is not the case, right? So so in some ways I'm working backwards. I'll say what I need to do is prove P, right? If I can prove P, then I got it, right? And then I kind of get stuck. How do I prove P? I don't know how to prove P. All right, so I come back to the beginning again. Right here, I had R or Q, right? And I kind of went backwards here. I could go back here and say, okay, what happens if I prove Q? Well, then look, how would I prove Q? Well, this is the only guy who mentions Q. If I could prove not P, then I would be done, right? So now I say, hey, if I could prove P or not P, I would be done. Oh, I can prove that, right? P or not P, that's a occluded middle, right? Does that kind of make sense? So in some ways, you were right. I didn't think I'd hack backwards, but I kind of hacked backwards. And there was really only one thing to do here, right? If we're just hacking forwards and backwards, right? In I do think the table's good because there's only so many things that you can do, right? And they all kind of make sense. If you look at other people's proof systems, well, maybe there are fewer things you can do, but they don't make sense to me, right? I wouldn't know how to use. When I first solved some of these proofs, I don't know how to prove this from these weird things, but they're good rules.